Imagine holding a blowtorch to a piece of wood for 5 minutes, and instead of catching fire, the board actually gets stronger. This isn't a magic trick or a sci-fi prop. It is the result of a massive breakthrough in material science from the labs at ETH Zurich. For thousands of years, wood has been our primary building material, but it has one fatal flaw. It's basically solid fuel. We've tried coating it in chemicals and soaking it in salts, but those methods often degrade the wood's strength or leach toxic fumes into the air. But engineers in Switzerland have found a way to change the game by turning sawdust, a waste product, into a high-performance composite that uses chemistry to fight back against heat. And the secret ingredient is hidden inside a common watermelon seed. To understand why this works, we have to look at what wood actually is, a complex network of cellulose tubes called pores. Usually, these pores are filled with air, which provides the oxygen fire needs to thrive and spread deep into the material. The engineering team at EMPA realized that if they could fill these microscopic voids with a fire-resistant mineral, they could create a physical barrier that heat simply cannot penetrate. But you can't just stuff minerals into pores that are only a few microns wide. They needed a way to grow the minerals inside the wood from the bottom up. This is where the brilliance of biomineralization comes in, using nature's own tools to build a mineral skeleton within the organic structure.
The researchers start with ordinary sawdust, which is usually burned for low-value energy or tossed into landfills. By mixing this sawdust with a specific mineral solution, they create a slurry that can be molded into any shape, from bricks to structural beams. This isn't just a coating. The entire material is transformed at the molecular level. It's a composite that combines the lightweight flexibility of wood with the extreme heat resistance of stone. The result is a material that feels like timber but behaves like granite. But the really clever part isn't just that it doesn't burn. It's how the material actively uses the energy of a fire to trigger a cooling reaction that protects its own core. To see how, we have to look at the chemistry of the watermelon seed. The team discovered that the enzyme urease is found in high concentrations in watermelon seeds. This enzyme acts as a biological catalyst, triggering a reaction that turns a liquid solution into solid crystals in a matter of hours. When this enzyme is introduced to a mixture of urea and mineral salts inside the wood, it starts building a mineral called struvite. This is the same stuff that forms in certain natural environments, and it is incredibly stable. This process is so efficient that it fills almost every microscopic void in the sawdust. By the time it's finished, the wood is no longer just wood. It's a mineral-reinforced polymer that is basically a biological ceramic. But how does a mineral skeleton stop a 1200-degree flame? The secret lies in the thermodynamics of the struvite itself. It's not just a passive shield, it's a chemical fire extinguisher that is built into the very walls of the building. The engineering here is absolutely brilliant because it solves one of the biggest challenges in construction, making sustainable materials that can actually survive a disaster. And they did it by looking at how nature manages minerals. Now that we've seen what the material is, we need to dive into the molecular engine that makes it all possible. It's time to look at the watermelon seed reaction and the struvite shield in action. The heart of this technology is a process called enzyme-induced carbonate precipitation, or EICP. It sounds complex, but think of it like a 3D printer that works at the molecular level, building mineral structures wherever the enzyme is present. The engineers at ETH Zurich chose watermelon seeds because they are packed with urease. When you crush these seeds and extract the enzyme, you're essentially getting a high-performance chemical trigger for free from agricultural waste. When this enzyme meets urea, a common nitrogen compound, it breaks it down into ammonia and carbonate. This change in chemistry causes the surrounding minerals in the solution to suddenly lose their solubility and crash out as solid crystals. These crystals don't just grow randomly. They anchor themselves to the cellulose fibers of the sawdust. It's like pouring concrete into a rebar cage, but the rebar is the wood fiber, and the concrete is grown atom by atom. The result is a material where the mineral and the organic fiber are perfectly integrated. This prevents the delamination that usually happens with coated fireproof materials, where the protective layer simply peels off when things get hot. Because the struvite is grown inside the pores, it actually increases the structural density of the sawdust board. It goes from a soft, crumbly material to something with the compressive strength of high-grade masonry. Now, here is the genius part.
Struvite is a hydrated mineral, meaning it has water molecules trapped inside its crystal lattice. When a fire starts, these crystals don't just sit there. They start a two-stage defense mission. As the temperature hits about 100 degrees Celsius, the struvite begins to decompose. This is an endothermic reaction, which means it actually sucks heat out of the fire to break its chemical bonds. Think of it like a built-in fire department. The material itself is sweating at a molecular level to keep its internal temperature from rising. But the water is only the first half of the shield.
As the water evaporates, the struvite also releases ammonia gas. This isn't enough to be harmful to people, but it is enough to create a gas shield that displaces the oxygen right at the surface of the wood. Fire needs three things: fuel, heat, and oxygen. The ETH composite attacks all three. The mineral replaces the fuel, the endothermic reaction steals the heat, and the ammonia shield chokes out the oxygen. This triple threat defense is so effective that even under a constant torch, the wood underneath the mineral layer remains below its ignition temperature. It's a self-protecting mechanic that requires no power and no human intervention. But creating a miracle material in a lab is one thing. Scaling it to build entire cities is another. To make this truly sustainable, the engineers had to find a way to source their minerals without mining them from the earth, and that led them to one of the most unlikely places imaginable, the local sewage treatment plant. Because it turns out, the ingredients for unburnable wood are hidden in our waste. Next, we're going to look at the industrial logistics of this circular revolution, how we can turn our sewers into the mines of the future to build the fireproof cities of tomorrow. The minerals needed for struvite, magnesium, nitrogen, and phosphorus are actually a major problem for wastewater treatment plants. If they aren't removed, they form rock-hard deposits that clog pipes and cost millions in repairs. By intentionally triggering struvite formation at the treatment plant, we can mine these minerals out of the water. This cleans the water, protects the pipes, and gives us the raw materials for our fireproof wood all at the same time. It's a perfect example of circular engineering. We're taking a waste product that causes problems and turning it into a high-value building material. No mining, no carbon-intensive transport, just pure resource recovery. The logistics are surprisingly simple. Sawdust from local mills is trucked to a central facility, where it's mixed with the recovered minerals and the watermelon seed extract. Because the reaction happens at room temperature, it uses a fraction of the energy of concrete or steel production. Traditional fire retardant boards often use brominated chemicals or formaldehyde, which can be toxic, but this composite is 100% bio-based. It's so safe that at the end of its life, you could theoretically grind it up and use it as fertilizer. This is because struvite is actually a high-quality, slow-release fertilizer. The phosphorus and nitrogen that protect the wood from fire are the same nutrients that plants need to grow. It's a building material that actually gives back to the earth. But the real impact is in the carbon math. Wood naturally stores carbon that trees pull from the atmosphere. By turning sawdust into long-lasting building materials instead of burning it, we are effectively locking that carbon away for decades. When you add in the fact that we're replacing carbon-heavy materials like concrete and steel, the environmental benefit is doubled. We're not just building safer cities, we're building cities that help heal the planet. This is the future of engineering, not just solving one problem like fire safety, but solving 5 problems at once. Waste management, carbon storage, resource scarcity, and structural integrity all addressed in a single material. As we scale this technology, imagine a world where our skyscrapers are made of timber that is as fireproof as steel, but as light as wood. A world where the very buildings we live in are made from the waste we used to throw away. The engineering behind this unburnable sawdust isn't just about fire. It's about a fundamental shift in how we think about materials. It's about moving from a world of take, make, and waste to a world that is truly circular. It's a reminder that the solutions to our biggest challenges are often right in front of us, hidden in a watermelon seed, a pile of sawdust, or even the water flowing through our sewers. The next time you see a piece of wood, don't just see fuel for a fire. See a complex biological machine that, with a little help from some clever engineering, can become one of the most resilient materials on Earth. We are entering a new era of living materials, where the line between biology and engineering disappears. And it all started with a simple question: how do we make wood forget how to burn? The engineering is brilliant, the chemistry is elegant, and the future is finally fireproof. Next time you see a watermelon, you'll know exactly what kind of power is hidden inside its seeds.